Welcome once again to the lecture number 5 of recorded e-sessions of digital signal processing. So as we are studying digital signal processing, our main focus is to discuss discrete time signals and how these discrete time signals is processed by discrete time systems. In the previous lecture, we have covered the classification of signals, and in that classification, one classification is discrete time signal 2. So let's discuss that classification in detail in this slide. So a discrete time signal, as shown in the slide, is basically a sequence of numbers. This type of discrete time signal arises naturally or can be produced with the help of continuous time signal. If this type of signal arises naturally, then you may take the example of situation such as amortization problem, or if you model national income, or if you are talking about the radar tracking, then obviously we will get the discrete time values. So the signal plotted against these discrete time values is a discrete time signal. But another category of obtaining discrete time signal is by sampling continuous time signal that is sampled by the data systems and digital filtering. So a discrete time system either obtained by naturally or by the sampling of continuous time signal is denoted by x of n, and we use the square bracket as shown in the slide 2 indicated by the pointer. We have to indicate a discrete time signal with square brackets, and if it is a continuous time signal, we denote it with the parenthesis. But as far as we are discussing about the discrete time signal, it is denoted by the square bracket. So discrete time signals can be denoted by x of n, y of n, z of n. We can take any variable, and the variable n always takes the integer value, and x of n denotes the nth number of the sequence labeled x. For example, there are two variables x and n. So n is the integer value and x of n is the value at that particular integer. For example, n is equal to 1 here, and x of n is the y-axis value or magnitude at instant n is equal to 1. So by using this notation, discrete time variable n is enclosed in a square bracket instead of parenthesis, because parenthesis has been reserved for enclosing continuous time variable such as x of t. So systems whose inputs and outputs are discrete time signals are discrete time systems. We will discuss discrete time system in more detail in the upcoming lectures. But for example, a digital computer is a very popular and familiar example of discrete time system. So a discrete time signal is a sequence of numbers, and a discrete time system processes a sequence of numbers denoted by x of n to produce another sequence y of n, generally as the output. We take generally x of n as the input, and this x of n is processed by a discrete time system. For example, you may take a computer and it will yield another set of integer values which is denoted by y of n, and that y of n is the output. So we generally take x as an input variable and y as a output variable. So discrete time signal, we have discussed that it can be obtained naturally or it can be obtained by the sampling of continuous time signal. So when we obtain a discrete time signal by uniform sampling of a continuous time signal which is denoted by x of t, so that type of discrete time signal can also be expressed as x of nt. Clear? That if we are obtaining a discrete time signal by the sampling of continuous time signal, then we can also represent that discrete time signal by x of nt, where t is the sampling interval, not the time period of the signal but the sampling interval, and n is the discrete variable and it must have some integer values. So x of nt actually denotes the value of the signal at time nt. So the signal x of nt, which is denoted as this, so this signal x of nt is a sequence of number. We may also name as sample values. So by definition, this is also a discrete time signal. So we have both the notation. We can, if we are obtaining the discrete time signal by sampling of continuous time signal, we can denote like this, and we have the margin, or we can denote the signal by this x of n, simply x of n or x of nt. So in this plot you can also see a discrete time signal. N is taken as the y-axis and x of n is basically the magnitude of the signal along the y-axis. So basically this is a continuous time signal. If we take a continuous time signal, for example exponential minus t, as shown in the expression to e raised to power minus nt. So nt is basically after the sampling of a continuous time signal which is continuous time and it has the variable of t. So e raised to power minus t can be sampled with this expression e raised to power minus nt, and if we sampled it at the time interval minus zero point 0.1 second, so we will get this discrete time signal as shown in the plot. This is the signal obtained for the expression e raised to power minus t, and it is sampled at the time interval of 0.1 and we will get this signal. So this type of discrete time signal is processed or can be processed by the discrete time systems, generally known as digital filters. So if we have a continuous time signal in general, we can first sample it and convert it into the discrete time signal, and that discrete time signal can be processed by digital filters, and we will obtain the output y of n. And now we have a choice, either we have to work with y of n, or we can again convert that y of n into continuous time signal y of t by a converter, DAC, which is digital to analog converter. Another very important aspect to calculate the strength or size of a signal is by means of its energy and power. By calculating the energy or power of a signal, we can predict or we can determine the size of a discrete time signal. The expression for calculating energy as well as the expression for calculating power of any discrete time signal is shown in the slide. So for a signal, for a discrete time signal, suppose we are calculating energy of a discrete time signal. So to have a finite energy of that signal, there must be some condition, and the condition is that the signal amplitude must tends to 0 as n tends to infinity. If this is valid, then we can calculate the energy of the signal, and the signal is called as the energy signal. But if the sum in this equation of energy is not converging, then we will not get the finite answer. For a finite value of energy, sum must be converging, and this will happen only if the magnitude tends to 0 as n tends to infinity. And if we are getting the finite value of energy, then we call this signal as a energy signal. But in some cases, when the amplitude of our signal does not tends to 0 as n tends to infinity, this might be the case that our signal magnitude does not decreases to 0 as n tends to infinity, then the signal energy will be infinite, as you can see from the expression. So what we will do? So in this case, a more meaningful measure of the signal is required, and that meaningful measure is to calculate the signal power by using the expression shown in the slide. So a signal power is mathematically defined by the expression. So in this equation you can see the summation x of n whole square, and its summation is divided by 2n plus 1. And why 2n plus 1? Because there are 2n plus 1 samples in the interval form from minus n to n. For example, if you are considering an interval from minus n to n, so how many samples will be there? 2n plus 1 plus 1, because n is equal to 0 is also there. Minus n to 0 is number of terms will be n, and 0 to n will be again n. So 2n, and n is equal to 0 is also a sample. So 2n plus 1 is the total number of samples in that interval, and the interval is minus n to n. So for periodic signal, you can imagine that we can calculate energy for a periodic signal, and if the signal is periodic in discrete time, so the time averaging needs to be performed for only one period. So after calculating the power from this formula, and the power comes to be finite and non-zero value, then that signal will be called as power signal. And similarly, like we have discussed for continuous time signals, signal may be a power signal or energy signal, but can never be both power or energy. So same will be true for discrete time signal. A discrete time signal can either be an energy signal or a power signal, but cannot be both at the same times. But there might be a case that any signal may be neither energy signal nor power signal. So this can happen. A signal may be energy signal or maybe power signal or none of these, but it is not valid that a signal may be both energy signal and power signal. So this will never happen. So I hope you get the idea how to calculate the energy and power of a signal and how to comment regarding if the signal is energy signal or power signal. Simply if we get the finite value of energy, then the signal is the energy signal, and if we get the finite power and non-zero term, then the signal is power signal. So let's understand this topic further with the help of an example. So here is an example how we can predict the or we can classify the signal as energy signal or power signal. We have two signals, signal A and signal B, and both are discrete time plots, and we are assuming the same pattern because we in the end we will conclude which signal is the energy signal and which signal is the power signal. We are taking the same magnitudes for both the signal, and you can see that the first signal is aperiodic and the second signal is the periodic version of the same signal. So the question is, find the energy of a signal x of n is equal to n if it is basically a ramp signal as shown in the figure A, and the power for the periodic signal y of n in figure B. So here it is already mentioned that we have to calculate the energy for the first signal. As you can see that we have a aperiodic signal, and we in the previous slide we concluded that for aperiodic signal we usually calculate energy, and if the signal is everlasting signal, then it is not possible to calculate the energy of a signal. So we will calculate power for that signal for a certain time interval. So here you can see that first signal is aperiodic and the second signal is everlasting signal. So for first signal we are going to calculate the energy, and for the second signal we are going to calculate the power. So let's start by solving the problem first by calculating the energy of the first aperiodic signal. In the first signal you can see that we have 1 2 3 4 5 6 sample values from n is equal to 0 till n is equal to 5, and at n is equal to 0 we have a value of 0, and at n is equal to 5 we have a magnitude of 5, and for similarly for n is equal to 1 we have a magnitude of 1 because it is a ramp signal. X of n is equal to n, so whatever the value of n, the same will goes to the value of magnitude. So total there are 6 terms from n is equal to 0 till n is equal to 5. So by using the formula for energy formula is E of x is equal to summation n square or mod of n square. And it is not necessary to take the mod because we are already squaring the values, so the result of square will always be a positive value. So I would like you people to calculate the energy of this signal. I already gave you the hint, and the hint is simply by applying the formula of energy, which is summation n square, and here n is equal to we will refer to the array x of n is equal to n, means we have 6 different values of n for each time interval. For n is equal to 0, value is 0, n is equal to 1, value is 1, n is equal to 2, value is 2, n is equal to 3, value is 3, and so on. So by applying this formula, you can easily calculate the energy of this signal. So take your time and try to calculate the energy of this signal. It is quite simple, not a very complicated signal, very simple signal. Try to use the formula I just taught you in the previous slide. Take your time to calculate the energy of this signal. I hope you come up with the result. Now come to the second part, which is part B. And in part B, what we have to do, we have to calculate the power of a periodic signal, and the signal is denoted by y of n, x of n. So here it is x of n. How we will calculate the power of signal? By using the same formula, summation n square, but now as you can see from the figure, we can not calculate the energy because it is not a converging signal. That is, values are not approaching to 0 as signal tends to infinity. So we can never calculate energy of such type of signal. So another meaningful measure we have studied is the power. So we are calculating power for this signal, and power is to be calculated for certain time interval which is equal to the periodicity of discrete time signal. So n here, which formula will you apply for to calculate the power? P of x is equal to 1 over 2n plus 1 multiplied by summation x of n square. So x of n is same just as in the previous example, and 1 over 2n plus 1 is added here. So you have to calculate or predict the value of n, and you can see that the value of n is 6 because after 6 samples the signal is repeating itself. So put the value in the formula and get the result of power. Take your time to calculate the power of signal. I hope you are getting my point. We are calculating energy for the first signal, and we are calculating power for the second signal, as we are unable to calculate the energy for second signal. I hope you all must done with your answer. So let's verify your answer. So the solution is shown in this slide. I hope you all get the same answer. from n is equal to 0 to n is equal to 5 n square, and it is the formula of energy. We will get 55, and for power we just divide this 55 by 1 over or 2n plus 1, and n is equal to 6 as discussed. The next topic for our discussion is some useful and important signal models in continuous time domain. As we are studying digital signal processing, so we are more interested in the signal models for discrete time domain. But for your convenience and feasibility, I will give you a brief overview regarding the signal models for continuous time domain. Afterwards, we will shift our focus to the models in discrete time domain. Because the models are almost similar with few differences and modification, so it will help you to understand the concept better. Starting our discussion with the first model, which is unit step function. Basically, in the area of signal processing, few signal models such as unit step function, unit impulse function, and unit and exponential function plays an important role. Not only they serve as a basis for representing other signals, that is, with the help of these signals, we can reconstruct or reproduce any complicated real-world signal. But also, these signals can be used to simplify many aspects in the area of signal processing. So the first signal is unit step signal or unit step function, denoted by u of t. In the previous lecture, we have discussed causal signals as that signals that begin at time t is equal to 0. So such type of signals can be conveniently described in terms of unit step function. And what is unit step function itself is, we can represent the unit step function mathematically as shown in the slide. U of t is equal to 1 for time t greater than and equals to 0, and u of t is equal to 0 for time t less than 0. So if we plot according to this mathematical expression, then we will get this plot as shown in the slide. This plot is for unit step function. So how this signal help us? Just take an example. If we want a signal to start at time t is equal to 0, so that it has a value of 0 for time t less than 0, we only need to multiply that signal by u of t, that is unit step signal. For example, if we have a signal e raised to power minus at, and if we are assuming this signal as an everlasting exponential signal that is starting from t is equal to minus infinity. So if such type of signal is present, and if we want to convert it into causal form, so the causal form of this exponential function e raised to power minus at can be described as, or can be represented as, e raised to power minus at into ut. That is, simply we multiplied that everlasting signal to unit step signal, and after multiplication we get the signal which is causal in nature, that is all the values before time t less than 0 becomes 0, and the signal only appears for time t greater than and equals to 0. The second important signal model in continuous time domain is unit impulse function. It is denoted by sigma of t. It is one of the most important function in the study of signal processing. This function is mathematically defined as sigma of t is equal to 0 for time t not equals to 0. We can visualize this expression as a tall, narrow, rectangular pulse having area of unity, and the area of unity is expressed by the mathematical expression integral minus infinity to infinity sigma of t dt is equal to 1. It means area under the curve is equal to 1. Unit impulse function always covers an area of unity. So we can visualize our signal as a tall, narrow, rectangular pulse of unit area. The width of this rectangular pulse is very small. You can see in the second plot we denote width by epsilon, and this epsilon tends to 0. If we are talking about ideal impulse, then this epsilon is equal to 0. That is no width of that rectangular pulse, and consequently its height is very large. That is 1 over epsilon tends to infinity. If epsilon is equals to 0, then 1 upon epsilon tends to infinity. You know 1 over 0 is equal to infinity. So rectangular pulse having very the width of that rectangular pulse is infinitely small, and the height of that rectangular pulse is infinitely large. Both are opposite, width and height. And another property of impulse signal is that the overall area that has been maintained by that rectangular pulse is unity. So we can say that sigma of t is equal to 0 everywhere except at time t is equal to 0. And what happens at time t is equal to 0? The function is undefined. So for this reason, a unit impulse signal is represented by a spear like symbol like arrow. So this is the reason that we represent unit impulse signal by an arrow. Sometimes we classify our signals as even signals or even functions and odd functions. This is to simplify our calculation. So what are even functions and odd functions? First of all, even function. The first plot is for even function, and even function has the same value at the instant t and minus t for all values of time. It means that function is symmetrical about the y-axis or vertical axis. As you can see from the plot also, that the function plot A is symmetrical about the vertical axis. But on the other hand, if you look at the second plot is for odd function, and odd function is one which at any time instant is the negative of its value at the time instant minus t. It means the function is anti-symmetrical about the y-axis or vertical axis. This what I'm trying to say, let's understand by looking at the plots. This is positive t and this is negative t. Similarly, in the second plot, this is positive t and this is negative t. So even function is one in which the positive values of time are symmetrical as the values for negative values of time. That is, along the y-axis function is symmetrical. Or in other words, how you can determine the function as an even function? If you draw the signal on paper and you try to fold the paper along the y-axis, then the signal must overlap. If the signal overlaps, then this signal must be an even function. Now come to the odd function. Similarly, as we discussed for even function, this is positive value of time and this is a negative value of time. So what must be the values of signal for positive values of time? The anti-symmetrical values must exist for negative values of time. Or in other words, you can say if you fold around y-axis or vertical axis, the signal must be mirror image of each other or each quadrant. Or another technique to verify signal as an odd signal is that if you fold the signal along the y-axis and then next fold this signal along the x-axis. Please listen it carefully that what you have to do. First you have to fold the signal along y-axis, then the signal appears to be some like this pattern, and if you again fold the signal along the x-axis, then the signal must overlap. So this is the indication of an odd signal. If you fold on both the axes, signal overlaps. So this is odd function or odd signal. There are some properties of even and odd functions. The first property is if we multiply even function with an odd function, the resultant function will be an odd function. The second property is if we multiply two odd functions, then the resultant function will be an even function. The third property is that if we multiply two even functions, then we will get an even function in the result. So note down these three properties, that even and odd, even multiplied by odd is equal to odd, odd multiplied by odd, resultant will be even, and even multiplied by even, resultant will be even. Means if we multiplied the liked function, then the resultant will be even function, and if we multiply the unlike function, then the resultant will be odd function. I hope that this topic is clear to you. So in this lecture we have discussed the discrete time signal, how we can plot it, how we can convert a continuous time signal into a discrete time signal. Not in detail but just an overview. We will discuss it in detail in the third week, which is sampling, analog to digital conversion. So in this lecture we have covered how to calculate the size of a discrete time signal. By size we mean to say the strength of a discrete time signal, and strength can be represented by means of signal energy or power. Then we solve a numerical regarding calculating the energy and power of a discrete time signal. Afterwards, we have discussed some important models in continuous time domain. So in the next lecture, we will cover inshallah the models for discrete time domain.